In the last part of the lecture, we will look at yet another example of a greedy heuristic. We will see another case where a greedy heuristic fails to find the optimal solution. I've chosen to give you an example of the assignment problem, since this is a problem we will look at again in the coming weeks. In this particular problem, you are asked to assign 4 tasks to 4 available employees. You know how long each employee takes to do each task, and you would like to find the assignment that minimizes the total time necessary to complete the tasks. Okay, so you have to find the best assignment here. What would you do? Well, the greedy heuristic we are going to look at today will sequentially pick assignments, so assign a person to a task based on the best available option in the table at the time the selection is made. So initially we will look for the assignment with the shortest duration. We will make that assignment, and then we will consider the reduced problem and pick the best available assignment in that table. Okay, so initially we would then assign person 2, task 3, and get the 3 hours there. That is the minimum value in this table. Once we've made that assignment, we would say person 2 is out of the problem, task 3 is out of the problem, and now I make the best assignment available given the remaining values. Okay, so the greedy approach is sequentially assigning tasks by choosing the person task assignment that gives me the shortest duration. I'm going to break ties arbitrarily. If you look closely at this table, you will see that there are quite a number of 6s here, so it's highly likely that you will reach a point in the greedy heuristic where you are forced to pick between 2 options that are equally good. So when we break ties arbitrarily, we just pick at random, if you like, any of the options that are equally good. So I skip most of the details of this greedy heuristic, but I just give you the solution here. So in the solution, you see person 2 gets task 3, person 4 gets task 1, person 1 gets job, I don't know why I say job there, I mean task 2, person 3 gets task 4. So this solution has an objective value of 21 hours. And we would like to know, is this optimal? Remember that a heuristic does not provide any guarantees on the quality of the solution it provides you. So we don't know if it's optimal, good, or bad. We can try to prove it, try to prove that this is in fact the optimal objective value, but we would fail in this case. So what we're going to do is come up with a mathematical formulation that will tell us the optimal value, and then we can look at maybe reasons why the heuristic failed. Okay, so let's build a mathematical model of this problem. Our aim is to assign people to tasks. So we will have a set of binary decision variables to indicate those possibilities. Xij will equal 1 if person I is assigned task j. I and j will run from 1 to 4. There are 4 tasks and 4 employees. Our objective value will minimize the total time necessary to do all tasks, and you should see a strong resemblance between this objective value and this table here. In fact, there's a decision variable associated with each cell of this table, and the variable has, let's say, the cost associated with that cell. Okay, so 8x11 corresponds to the 8 hours being selected if person 1 does task 1 or not. Okay. There's one constraint for each task. We need to make sure each task is done exactly once. So this constraint here is for task 1 and ensures that exactly one of persons 1, 2, 3, and 4 does that task. There are 3 other constraints of this type corresponding to tasks 2 through 4. If these were the only constraints we included in our model, then it would be possible for a task or 2 tasks to be assigned to the same person. So here we want to ensure that each person does exactly 1 task, and we need a constraint of this form. Okay, so this constraint just says that person 1 does 1 of the available tasks, and there are 3 other constraints of this type corresponding to persons 2 through Here's some example Julia code that you can use to solve this assignment problem. We start out by declaring a model. This is our cost array. It's essentially the table you saw on this slide related to the example. We have a parameter 4, which specifies that we have exactly 4 employees and 4 tasks. I define 16 binary variables here. My objective value sums up the binary variables, where each binary variable is multiplied by its corresponding cost. And here are my 2 types of constraints. The first type ensures that each person gets exactly 1 task, and the second set of constraints ensures that each task is assigned exactly 1 person. Okay, we can optimize that to give us the following optimal solution. In this case, the optimal solution has a value of 20, and it shows that our heuristic approach is good, but it does not return the optimal solution. The optimal solution actually has person 1 doing task 2, person 2 doing task 4, person 3 doing task 3, and person 4 doing task 1. And if you look closely at this, person 2 does task 4, and in the heuristic, we said person 2 would do task 3. And if we look at the table, that is the lowest cost entry in our cost matrix. So the greedy heuristic prefers to select this initially because it is a locally good thing to do. It's the cheapest option available. However, in the optimal solution, we actually need to assign person 2 task 4. Okay, so this is an example of where the greedy heuristic lacks foresight. When selecting task 3 for person 2, we were unable to see the implications of that decision until later. But exactly at that point where we select task 3 for person 2, we remove the possibility to get the globally optimal solution. Okay, so while that assignment is locally optimal, which is the cheapest thing to do at the particular time you consider it, what you really need to do at that point is to pick something suboptimal to get the globally optimal solution. Okay, so that's what we mean by lacking foresight. Okay, just to also introduce to you what is meant by the assignment problem in general and the generalized assignment problem. I've included a general description here. The type of problem is known as an assignment problem. You aim to find the best assignment. Typically, you match tasks with agents. Here we looked at people to tasks. It could be taxis to people. It could be jobs to machines. It could be lectures to lecture rooms, whatever. Typically, whenever you try to find a matching between 2 sets, you are solving an assignment problem. And the objective value typically maximizes some profit function of the assignment. And we try to ensure that each task is covered exactly once and each agent is assigned exactly once. Okay, and our binary variables are specified here. In 2 weeks or so, we will revisit the assignment problem and look at some of the structures of this problem and see why it is actually very easy to solve problems of this type. The generalized assignment problem is just a variant of the assignment problem where the number of tasks and agents may vary. So you could have more tasks than employees, for instance. Typically, it is also possible to assign multiple tasks to an agent, but in that case, each agent will have an available budget, if you like. So if the agent could do multiple tasks, then the person has some quota of hours that cannot be exceeded. Okay, so it's just a generalization of the assignment problem. Okay, that brings us to the end of today's lecture. I hope now you have a better feel for heuristics. I would like you to be able to understand and explain the difference between a heuristic approach and an exact approach. The key point here is that a heuristic typically does not guarantee optimality. I want you to know what a greedy constructive algorithm is. I want you to be able to design a greedy constructive algorithm. So identify a greedy aspect in the selection step of the construction algorithm. And I would like you to be able to give examples of when a greedy algorithm fails or succeeds in finding the optimal solution. And we've seen an example today where the greedy algorithm finds you the optimal solution for something like the activity selection problem. And we've seen two cases where it fails. Okay. If some of the material was a little bit difficult or you have any questions, please do not hesitate to get in contact with me. I'm more than happy to help. Thank you.